we already know some really awesome techniques for solving systems. It's just that our techniques were solving systems of linear equations. That's okay though. We are still going to use the exact same techniques to solve systems of nonlinear equations. That just means not all the equations involved will be lines. Sometimes they will be, sometimes they won't. Just a reminder, a system is when we have more than one equation. In this case, we're going to be looking at two equations. So we'll have two equations. And when we solve systems, what we're looking for is the intersection. So we used to look for the intersection of two lines, and then we would say, yay, we found the solution to that system. Now what we're going to do is look at the intersection of things that are not lines. I'm going to give you a clue as to what shapes you're going to be seeing. Think about what we've been learning. Conic sections. So we might have a system where we have a circle and it's intersected by a parabola. How many lines of intersection is there here? Or how many points? Looks like 4 of them. We could also have another situation where we maybe have a hyperbola and an ellipse. There's our ellipse. There's our hyperbola. Pretend it's touching. In this case, it would have 2 points of intersection. So we're going to be able to have more than just one solution, and some of our systems will. Just like before though, systems can have no solutions if they never touch at all. So the number of possible solutions we're going to be looking at in this video is 0. They could touch just once. 2, 3, and 4. So these are all of our possibilities. We could also have infinite if we happen to have an equation that represented the same circle or something like that. So it's going to be important for us to keep track of all the different solutions to these systems so that we make sure we don't lose a point, because these systems are really important when it comes to thinking about satellites in orbits, as well as satellites receiving information, such as the television satellite that you have on top of your house. So let's solve some systems of nonlinear equations using our methods that we learned in linear equations. Remember, those methods were substitution and elimination. Substitution is where we looked for a variable that was all by itself, and elimination is where we looked for opposites. We're going to do the exact same thing here, it's just we're going to have a lot more solutions this time. If we look at these two equations in this particular system, we see that one of the equations is a line, because it just has x and y, nothing squared, so we could rewrite it as a y equals equation. And the second equation is a circle, because we have x squared plus y squared equals r squared, which is 25. In fact, we could actually sketch a graph of this if we wanted to, so we could kind of think about what we know about this problem. We know that our circle is going to go out 5 from the origin. And we know that our line, we can use our intercepts if we want. We would have an x-intercept and a y-intercept of 1. So there's the sketch of our line. So we're going to be looking for 2 solutions for this problem. Now, we can use elimination or substitution. However, we can only use elimination if the variables are like terms, and x squared are not like terms. So I'm going to rewrite the first equation so that I can use substitution. We rewrite the first equation, it doesn't really matter which one you do it for. I'm going to say y equals negative x plus 1. Now I have a variable all by itself, and the variable all by itself is y. So what I'm going to do is substitute this x plus 1 for y into the second equation. So we have x squared plus negative x plus 1 squared equals 25. Good thing we spent all that time distributing, because that is what we are going to have to do in this problem. we have x squared plus negative x plus 1 times negative x plus 1 equals 25. So this means x squared plus, use your distribution, we get x squared minus x plus 1 equals 25. Now I'm going to combine like terms. The x squareds can go together, the x's can go together. So we end up with 2x squared minus 2x plus 1 equals 25. Oh my goodness, this is going to be a quadratic problem. So we need it to equal 0. I know you guys are groaning going, oh, we have to do this again? That's why I taught it to you in the first place. X squared minus 2x minus 24 equals 0. And there is a GCF, so let's do that first. The GCF is 2. We can just totally factor it out. Divide the entire equation by 2, and we don't have to worry about it anymore. So we get x squared minus x minus 12 equals 0 divided by 2, which is 0. So let's try to factor this. We want to think of numbers that multiply to be negative 12 and add to be negative 1. Probably going to be 3 and 4. If we want them to add to be negative 1, the 4 has to be negative, so the 3 is positive. So we have our two solutions. We have x equals negative 3, and we have x equals 4. Now these are just the x's. We need to find the y's. And the way we can find the y's is by going back to our original equation. Doesn't matter which one. I'm going to choose this one right here. Put a big circle around it so you see what I'm doing. We need to plug in each of our x values to find out the corresponding y value. So we know that y equals negative x, so y equals 3 plus 1. So when x is negative 3, y is 4. That's one of our solutions. I'm going to write it up in the corner. When x is negative 3, y is 4. Now our second solution will come because y equals negative x, so negative 4, plus 1, which equals negative 3. So our second solution is when x equals 4, y equals negative 3. Look at the graph that we sketched. Those points look pretty accurate, even based on just my little sketch. We know we have 1 down in the fourth quadrant, and we have 1 up in the second quadrant. So it's all kind of coming together. We're using systems, and we're using conics, and we're using quadratics to find these solutions to these systems of nonlinear functions, or nonlinear equations, sorry. So here we have another pair of equations. One of our equations looks like that same circle again. The other equation, the second one, well, I'm going to rewrite it as y equals negative x squared plus 5. That's actually just a nice little vertical parabola. So I'm going to draw a sketch of my graph so I know kind of what I'm looking for in this problem. We have that circle again going out to 5. And this is a parabola that has a vertex at 5 and it opens down. So approximately how many solutions are we looking for in this case? Looks like we might end up with 3. Now, I converted that second equation, so it kind of makes sense to use substitution in this problem. We don't necessarily have to, though. If we substituted in for y, we would end up with an x to the 4th. Another thing we could do is, if we had changed this equation by dividing by negative 1, we could have said that negative y plus 5 equals x squared. Now we can substitute in for x squared in the first equation. I'm going to try that just because it's something different. So negative y plus 5 plus y squared equals 25. So to rearrange things a little bit, we're going to get y squared minus y plus 5 equals 25. And haha, another quadratic. Let's move that 25 over so we have equals 0. Y squared minus y minus 20 equals 0. And let's see if we can factor. We're looking for numbers that multiply to be negative 20 and add to be negative 1. Probably going to be 4 and 5. And which one would be negative? 5. So this means we have two solutions. We have the solution of y equals negative 4, and we have y equals 5. Now these are only parts of the solutions to these problems because we're looking for points. Now we need to plug these back into the equation we didn't really use. So I'm going to go back up to the top, and it doesn't matter which one we choose to use. We can use the y equals equation, we can use the x squared equals equation, we can use the y minus 5 equation. They're all going to get us the same thing. Just for fun, I'm going to use the y minus 5 equation. So, y minus 5, negative 4 minus 5 equals negative x squared. So, negative 9 equals negative x squared. Divide everything by negative 1. So you have 9 equals x squared. So x equals plus or minus 3. Now let's think about what that gave us. That gave us the solutions for y. So that tells us if x is 3, y is negative 4, and x is negative 3, y is negative 4. So that's two of our solutions. Now let's go ahead and substitute in with the 5. I'm going to use the same equation that y minus 5 won. So 5 minus 5 equals negative x squared. 0 equals negative x squared. Divide both sides by a negative, so you get 0 equals x squared. So x equals 0. So in this case, we only had one solution, so when y is 5, x is 0, and that makes sense based on the graph that we originally had. So these are my three solutions, and you can see that 0, 5 is up there at the top, and then those other two, it looks like they're in the right place as well. Oh man, this system has some big numbers in it. Let's kind of think about what shapes we have going on though. For the first one, we have an x squared term, a y squared term, and the coefficients are different. This means it's an ellipse. For the second one, we have the same thing except a minus sign in between. So this is a hyperbola. If you think about an ellipse and a hyperbola, we could have up to 4 solutions for this problem. So let's go ahead and algebraically figure out what those are. You can convert both of these to graphing form, sketch a graph of them, and that would be a very smart thing to do. I'm going to start by finding the solutions first, and then we'll look at the graph. So we can actually use elimination as one of our solving techniques. And I am going to eliminate because I have almost opposites. We have x squared, we can cancel some of those out. So I'm going to choose to multiply the second equation by negative 1. So this means I have negative 25x squared, positive 16y squared, and this equals negative 400. Now if we ignore this one for a minute, let's add the two equations that we have left over together. 25x squared and negative 25x squared cancel. 9y squared and 16y squared is 25y squared. And 225 and negative 400 is going to be negative 175. Alright, so now divide both sides by 25. We're going to have y squared equals negative 7. Now, I want to ask you a question. Is it possible for y squared to ever equal a negative number? Nope. So, this problem actually has no solutions. That's okay. Now, let's think about what this could possibly look like. For that first ellipse, we will end up with the equation x squared divided by 9 plus y squared divided by 25 equals 1. How do I know that? I divided by 225. So this is up 5, down 5, right 3, left 3. There's our ellipse. For a hyperbola, we're going to end up with the equation x squared over 16 minus y squared over, that's y squared, I swear, over 25 equals 1. So this hyperbola has its branches at 4, 0. So you can see these guys never cross. So this system happens to have no solution. Alright, so this system of equations has a line and it has a parabola. Since we have a line and a parabola, we can have at most 2 solutions. Let's use an algebraic technique to find these solutions. Looks like we already have y equals something, so I'm going to use substitution to plug in 3x plus 3 for y. That means we have 3x plus 3 equals x squared minus 4x plus 3. So we have another quadratic. We need to get equals 0. So to get equals 0, we can subtract 3x and subtract 3 from that side. On the other side, I'm also going to subtract 3x and subtract 3. So we end up with the equation 0 equals x squared minus 7x. Looks like those cancel and we get 0. We can still factor this. This has a GCF. So when we factor this, we're going to get 0 equals x times x minus 7. When we solve each of these factors for 0, we're going to get x equals 0. And this second one will get us x equals 7. This kind of makes sense because if you look at your line and you look at your quadratic or your parabola, they both have a y-intercept of 3. So x equals 0 makes sense. The parabola will go through 3 and the line will also go through 3. That would be one of the solutions. So let's plug that in to verify it algebraically. We know x equals 0 is one of the solutions. Let's plug it into one of our 2 equations. The top one is a little easier, so that's the one I'm going to choose to use. So we get y equals 3 times 0 plus 3. So we get y equals 0 plus 3. So we get y equals 3. This means that one of our points of intersection is 0, 3, which we knew because they had the same y-intercept. Now let's find the other point of intersection. That's going to be where x equals 7. So again, I'm going to plug it back into that equation. Y equals 3 times 7 plus 3. And we get 21 plus 3, so we get 24. That means our second point of intersection is the point 7, 24, which again makes sense. I can't see it on my graph, but the line would continue to grow, the parabola would continue to grow, and they'll hit again at that particular point. So the intersection of this parabola and this line happens to be 2 intersection points at 0, 3 and 7, 24. Alright, this is the last system we're going to look at. This is another system of a line and a parabola. Again, it looks like substitution is going to be the best method for this one. We already have y equals, so we can substitute for y into the second equation. So we get x minus 2 equals x squared minus 4x minus 2. Quadratic, we need equal 0. So to do that, I'm going to subtract x from both sides, and I'm going to add 2 to both sides. So subtract x, add 2. Now our equation is 0, because these both cancel, equals x squared minus 5x, and, these cancel too. So this is just like that last example. We can factor out the x, and we have x times x minus 5. We're done because we have no more squared terms. Now if we solve each of our factors for 0, we're going to get x equals 0, and for the second one, we're going to get x equals 5. Now again, let's look at these two equations. They both have the same y-intercept. Now that makes sense that we get x equals 0 because they're going to cross at the y-intercepts that they share. So let's plug these back in algebraically and see what we get. I'm going to choose to use the first one. Y equals 0 minus 2, so y equals negative 2, which means one of our solutions is 0, negative 2, which, like we said, we understand that because the y-intercepts are exactly the same. They are going to cross at that point. Now if we find the second one with the 5, we get y equals 5 minus 2, so y equals 3. So that means our second solution is when x is 5, y is 3. Lines and parabolas are probably the ones that we're going to look at the most because we're going to be looking at signals intercepting parabolic receivers. They're probably one of the most widely used systems of nonlinear equations because the satellites and receiving information is a very common occurrence in real life.